Hello, everyone. Thank you for joining our session. We now introduce Andre-Michel Ferrari, a senior specialist with reliability engineering at Enbridge Pipelines. He'll be helping us understand building a P through F curve using reliability engineering principles. Okay.
Good day, reliability and maintenance fellow professionals. My name is Andre Ferrari, and today I'm going to talk to you about reliability engineering and building a PF curve using reliability engineering principles. First of all, I'd like to thank the LRVS 2022 Conference Organizing Committee for inviting me today, and specifically Sanya Mathura, who's not only a great organizer, but also an outstanding colleague in the world of maintenance and reliability engineering. So jumping in, as part of this presentation's objectives, we will introduce reliability engineering concepts, and then we'll use those concepts to build a PF curve. And finally, I will briefly showcase an example of a PF curve applied to power transformers. The reason why I'm introducing reliability engineering principles is because when I do a reliability study, there's a vast amount of information that comes out of the study, which can satisfy different needs in the organization. So from supply chain to maintenance planning via designs or budgeting. In our specific case, we can extract some of the learnings to build a PF curve, and I will showcase this today. So 20 minutes is a short time, so we will be flying at 10,000 feet, so fasten your seatbelts. When we do a reliability study on an asset, we typically use lifecycle records such as failures or specific performance parameters of interest to us. In this example here, we have a set of new light bulbs lined up and ready to go on a test bench. We switch them on at time 0 and record the time to failure for each of the light bulbs. We can see that the individual units fail at different intervals. Some will fail early, some later, and some will not fail at all at the end of the test. In essence, the failure interval will provide us with the life characteristics of the population of light bulbs and how a typical light bulb will behave over its life cycles. The next step is to define the statistical distribution or model that will best represent the life cycle of this asset. Typical distributions may be Weibull, log normal, or non-parametric distributions that provide eventually the best fit for our data. Once we have the best life model, we can make the model work for us by doing some mathematical transformations to this model. And we end up with what I quoted earlier as the variety of information that can be used to inform different individuals in an organization and help them make the best decisions. We are trying to predict what the asset is going to do in the future. So for example, we can have in this case, as the graph here shows the probability of failures, we have 70% chance of failure after 900 days of operation of a typical light bulb. Or we can expect 2 failures after 1500 days of operations, which means that I have to budget for 2 spares in this interval of time, and so on and so on. Lots of information coming out of this study. So moving on, we talk about repairable systems in this presentation. 2 distinct types of assets or systems are generally studied in reliability engineering: the non-repairable system versus a repairable system. And it's important to distinguish between the two because the mathematical treatment of those 2 types are different. In other words, mixing them up would lead to the wrong life cycle model being used, hence incorrect results. Non-repairable systems are shown above here in the first section. Like a light bulb mentioned earlier, non-repairable, when failed, are replaced by a brand new light bulb, implying that the life of the component will be the same as the life of the previous light bulb, if you want. Conversely, repairable systems like a car, which is in this section here, we usually fix one component at a time, but the failure of this one component influences the longevity of, the life, if you want, of the overall system or car. For example, the failure of a bearing in a car influences the life of the car because it causes premature aging in the system. So when one component is replaced, the life of the system, or if you want, the next failure interval will be shorter than the last one, as represented in this diagram. So in essence, failures in a repairable system will happen more and more frequently over time. I have highlighted those 2 types of systems because they are important when we do a PF curve. And we need to indicate how we treat the data, and because this will eventually influence the correctness of our PF curve. Additionally, we talk about non-repairable system being as good as new when replaced, whereas in a repairable system, the system is as good as old when repaired. Now let's jump directly into what is a PF curve and what it is used for. This is a classical PF curve with asset life consumed on the horizontal axis, or it represents the time since the system started operating. Whereas the vertical axis indicates the health or condition in which the asset is at any moment in its life. When the system is at its end of life, to the right, the health index is 0. When we install or commission the system at time 0, the health index is considered at 100%. As we move from time 0 onwards, the condition degrades and we successively get into lower health indexes measured between 0 and 100%, represented by H1 and H2 here. The intent of a PF curve, mainly in the world I work in, is to indicate what we call the PF interval, which is the time from an advanced degraded condition, let's say C2 here, to the time when we, which can be qualified as the end of life of the asset or the asset in question. A degraded condition like C1 or C2 means that the asset has deteriorated, but it has not yet stopped functioning. So it's still producing, it's still working, it's still pushing product through, if you want. Whereas the failed section, it's basically not functioning at all, or if repaired, will fail soon after. Hence, the PF interval informs the operator after he reaches a detectable degraded condition, in this case C2, how much time he has to initiate an action to mitigate the total loss of the asset. The mitigative action could be a repair, a restoration task, or it could be entirely replacing the asset itself. There are intermediate earlier detectable conditions like C1, which give yet advanced warning of degradation without losing function, and which might be useful to an operator as another warning signal. So moving on, this slide highlights the important principles around the PF curves. To get F, C1, or C2, as shown on the curve here, we use reliability engineering principles defined earlier, where each of the three values are characterized by a unique statistical distribution. In other words, they each have a unique distribution because they are statistically different. For example, C1 is obtained from infrared inspection, C2 from a vibration inspection, and F from a functional, basically from functional failure records, if you want. As mentioned earlier, points C1 and C2 represent degraded conditions, but in those conditions, the asset is still functional. The point F, or end of life, is a state where the asset is not functioning, or it's in a state which doesn't make financial sense to repair. For example, if the failure rate is too high, that is too many failures occurring in a short interval of time, it doesn't make sense. It does not make sense to repair the asset and it had reached a point in its life where the failure increase or the failure occurrences are cost prohibitive. C1 can be used for benchmarking purposes as it offers limited information with regards to the PF interval. Items that hit C1 earlier or eventually C2 can be flagged as potential bad actors. As mentioned, condition 2 is a more crucial measure to establish the PF interval. Now we are going to talk about a specific example which I have used in the past to define PF curves. And the example is based on power transformers. Power transformers are crucial in various industries. For example, in my industry, pipeline industries, as we use a lot of electrical power to run pumps, the pumps are used to push product through our pipelines. So transformers are seen as highly critical assets, and therefore their condition is monitored very closely. One of the condition monitoring programs, as shown on the left of this slide, is a dissolved gas analysis, or DGA. DGA consists of extracting an oil sample from the main tank of the transformer periodically and analyzing the 7 gases as illustrated in this oil drop here. The basis of the analysis is provided by the IEEE standard C57.104. The standard highlights the importance of each of the molecules in the oil and their thresholds of concern. In my case, transformers don't fail frequently, which is a good thing for the operation, but a not so good thing for me, the reliability engineer, because I lack maintenance records to do my analysis. So to obtain the end-of-life threshold for transformers, I turn to literature research papers, as shown on the right-hand side of this slide. So I have a 2-step process to calculate the end-of-life, or F point, on my PF curve. The number one, like in the middle here, I use a published industry benchmark for power transformers end-of-life, which is a failure rate of 0.05 failures per year. And the number 2 input is I use a Weibull statistical distribution obtained from the above mentioned publication, representing the typical life distribution, if you want, of a population of transformers. So the Weibull distribution provides a scale parameter, or beta, of 8.37, as shown here in red, and a shape parameter of 67.38 years. And if I inject the end-of-life criteria of 0.05 failures per year into this life model, or the Weibull distribution, I get an end-of-life value of 59.55 years, close to 60 years if you want. So in doing so, I have my F point on my PF curve, which I will illustrate on the next slide. So in this study, we use only one condition monitoring method. And so we obtain only one condition point on this PF curve, if you want, other than the end of life F point as shown here, right? The condition threshold illustrated here is based on DGA status 3 as defined by the IEEE standard. The coordinates of this P point is established at the health index of 72%, 0.72, and a lifetime of approximately 50 years. Hence, if the end of life point is 60 years, then the PF interval is around 10 years, as written here. Therefore, when I hit the P point, I have 10 years to plan a mitigation in order to avoid the F point or the loss of my transformer. I will give some further explanation of how the P point is obtained a little bit further in this presentation. I just want to stress that the P point is purely illustrative here, and I'm not authorized to share my company's records or data, and I will invite the audience to do their own calculations rather than taking my number and applying it to their system. So moving on, this slide illustrates a couple of examples where the actual P points are obtained. So the actual, we're going to compare actuals to the typical population of transformer defined statistical P point, if you want. Because the transformer is a repairable system, the actual P point obtained here the first time the DGA status 3 is achieved in those two transformers here. Transformer A is defined as a bad actor because the actual P point is 30 years earlier than the typical P point, which is 50 years. So for transformer A, the PF interval of 10 years still applies. So the end of life of the transformer is pretty early, so it's 30 years. So half of a typical transformation of a transformer. So that's why it's a bad actor. Transformer B is more in line with the normal population, even though its end of life is earlier. The idea is with those two transformers, benchmark their actual performance with the general population of the transformer. So that's how I apply this PF curve in my role. So this slide illustrates how the P point is calculated, as well as how the health index for the P point is calculated. There's a little bit of a mouthful here. A statistical distribution is obtained for the DGA status 3 occurrences, which is considered as a repairable system, the transformer being a repairable system. The P point is defined as the 90% probability of achieving status 3, which in this case is 50 years. So in other words, there is a 90% probability that the P point will be achieved at the 50-year mark. The health index is essentially a ratio of failure rates, where the end-of-life failure rate of 0.05 failures per year, which we defined earlier, becomes the reference point. Therefore, the P point health index is obtained by putting 50 years in the end-of-life distribution, the famous Weibull distribution I defined earlier, and obtaining the failure rate at the same 50 years. So if we do that, we inject the 50-year mark into the EOL distribution, the failure rate becomes 0.014 failures per year. As shown on the left-hand side here, we have this ratio of 0.014 divided by 0.05, and we subtract it from 1, and that's where we get the 72% as the health index at the 50-year mark. So this is a bit of a mouthful, I'm sorry, but it shows that there's rigor in how the health index is calculated. And in this case, the reference point is the end of life distribution. So we can have other points in the same way defined by other conditioning methods in this PF curve, but I will not go into that further. So to conclude, in this presentation, there are a few takeaway points, which I'd like to highlight. As demonstrated in the last slide, in the previous slide, the health index calculation methodology must be robust. We must avoid throwing numbers out there, and there must be some rigor in the calculation. The PF curve is fairly versatile and can be used for budgeting. So how much money I'll have to put aside to budget once I hit the PF point. It can be used for planning work. If we have hit the P point, we can plan the oncoming mitigation task based on the PF interval time defined. For example, transformers are not off-the-shelf items, and their replacement requires complex logistics. So the PF interval is crucial to give us time to do this. Finally, we can use the PF curve to identify signs of early degraded condition that is before the typical P point, as I've shown earlier. I would recommend doing a PF curve for as many different repairable assets as possible, rather than having a one-fit-all approach. Obviously, that means more studies and more maintenance records at our disposal. And finally, on a side note to this community, I'd just like to invite you to treat your maintenance and asset records like gold. They are very, very precious, and you'll be amazed what information a reliability engineer can provide you by crunching your maintenance records. And with this, I thank you all for listening, and I will now take questions.
Thank you, Andre, for a wonderful presentation on helping us understand PNF curve principles. We're open up for questions. If anyone has any questions that Andre could answer, please submit them in the chat box, and we'll go from there. All right.
All clear. Clear as mud. If there's no questions, I'd like to make a comment, but I'll still wait, right?
Let's wait a couple minutes.
Yeah.
Sure. Okay, we have a question from Musa Ladley. His question is, when should we take actions when reach the potential failure? I
Uh,
mean, in regard to P&F interval.
yeah, great question. Thanks, Musa. I guess as soon as you hit the P, you start planning, and you hit the P point, you start planning because, as I said earlier, things like transformers, they're not off-the-shelf items. You go buy them in Costco or Walmart. So you have to order them in advance. They custom manufacturers, and like going back to my industry where they really critical. So you have two plastics for taking the transformer out. So going offline from a power standpoint and then putting a new one in. So there's a whole bunch of work that needs to be done. And, getting money from accountants, no disrespect for them, takes a long time. For probably a few $1 million there sometimes to get a new transformer. So in my example, you have 10 years to do that, right? Now, if you can get everything sorted out in 5 years, good for you, right? But it just gives you 10 years to do the work and going back to planning immediately as soon as you hit the P point.
Excellent question, Musa. Thank you very much. Andre, whenever you're ready.
Yeah, and talk about slide number 9, where you have the two examples, and the example on the maybe I can show it on my screen. Uh, Let me, I don't know, see it. Sorry, I might have problems. Sorry about that. Should have
No
loaded
worries.
it. Okay. I'm trouble. But if you go to slide number 9, which is the two examples of one is a bad actor on the left, you can argue with me that I left the PF interval at 10 years, and because it's a bad actor, it's got to hit the P point earlier. Why should I leave it at 10 years? Well, it is already a bad actor. It's hit its P point very, very early, and you might want to take action right away and consider, it could fail in 5 years too. But there again, because it's a bad actor, it's a known bad actor, you might want to take action right away, or do something a little bit more pressing to deal with it, because it will not last. That's the comment I wanted to make.
Thank you. Thank you very much, Andre.
Okay.
Let's see. Any more questions? Oh, Andre, if you don't have anything else to add, I think that was a wonderful
Yes,
presentation.
thank you very much,
I mean,
everybody.
yeah, very
Thank you
interesting.
very much.
And one more
Oh,
from Pierre
see it
Luc.
coming in.
Yes. Okay. So here's the question. Besides the DGA, are there other procedures that can provide information to estimate the end life of the transformer?
So DG condition, right? End of life is defined by like failures, like it's broken, right? So DGA will give you the condition of the transformer, the internal degradation of the transformer, let's say, right? And but as I mentioned earlier, condition points are points they are, yes, the transformer has degraded, but it's still functional. It's still working. It's just giving you a little flag there. I'm not doing too good. I've got fever, right? So end of life is specifically a failure. It's just broken down or just keeps and over again. Now, if your question is about are there any other transformer conditions that you can use? Yeah, absolutely. If you can use other types of analysis that we do on the transformer, maybe paper analysis, fewer analysis. In this case, DGA worked well for me.
Thank you. Excellent question, Pierluigi. Excellent question. Let's see if there's anyone else that wants to insert a question before we end the session. Okay. Well, everyone, thank you very much for your time. Please network, share your ideas, contact information, and we'll see you back a little later. All right? Thank you very much, Andre. Wonderful work.
Thank you. Bye.
Thank you all. Bye-bye.